Alright, good morning, regular chem. As you can see, I am on my own this morning just for this first half. Mr. Kane was busy and could not join me on this portion of the video, but he will return shortly. So I'm going to tackle this one all by my lonesomes. This is Unit 10. This is called Aqueous Reactions, and what we are basically going to focus on is double replacement reactions, salts in water. Water is our most popular solvent. It is what we use most often when we make salt solutions. You have, on numerous occasions, made salt solutions in class, and you always use water to dissolve and dissociate your salt in. So aqueous indicates water, and reactions means that we're going to look at different types of reactions in water. Alright, the goals for Unit 10. You are going to use solubility rules, which are going to be given to you, and probably should have been given to you already, to determine if an ionic compound, and this entire unit revolves around ionic compounds. You are going to use the solubility rules to determine if an ionic compound is soluble or insoluble in water. You are going to predict the products of a double replacement reaction, because that's what this entire unit does, is double replacement reactions. You've already been taught how to recognize double replacement reactions, and you've already been taught how to predict the products of a double replacement reaction. Now we're going to bring all that together, and we're going to predict the states of matter of a double replacement reaction based on solubility rules, and then we're going to learn how to write molecular, complete ionic, and net ionic equations for double replacement reactions. So a lot of this you've had already, particularly the part about double replacement and predicting the products. What's new here is you will be predicting if a precipitate will form or not in a double replacement reaction using the solubility rules. Alright, general solubility rules. Don't memorize the handout. Just learn how to read it. It is a list of rules. The top half are solubles with exceptions. The bottom halves are insolubles with exceptions. Okay, soluble. What does it mean for an ionic compound to be soluble? For an ionic compound to be soluble, that means you place the solid ionic compound into water, and the ionic compound will dissociate into its representative ions. What does it mean to be an insoluble ionic compound? An insoluble ionic compound will be placed in water, but it will not dissociate. It will sink to the bottom of the beaker. It will stay a solid. Will the following be soluble or insoluble based on solubility rules? With your solubility rules in front of you, you are going to determine if the following compounds are soluble or insoluble. First off, you can usually focus on the anion end, because if you look at your solubility rules briefly, you will notice that the vast majority of the list focuses on the anion. And most of them polyatomic anions, but there's a few monatomic in there. I see chloride, bromide, iodide, and sulfide. Right? So most of the time you're going to look at the compound and determine solubility based on the anion. Alright, so here's our first example. A ionic compound, metal and a nonmetal, sodium's a +1, nitrate's a -1, written appropriately, this is sodium nitrate. Sodium nitrate, the solid, is placed in water. Will the sodium nitrate dissociate into the sodium ions and the nitrate ions, or will it stay as a solid and just sink to the bottom of your beaker? Based on solubility rules and focusing on the nitrate, the very first line of your solubility rule states that nitrates, chlorates, and perchlorates are generally soluble, meaning that sodium nitrate will dissociate into its ions when it is placed in water. I don't even have to look at the anion. Anything attached to group 1A and ammonium ions will be soluble without exception, without fail. And it's just a little trick, especially revolving around the group 1A, lithium, sodium, potassium, rubidium, and the ammonium cations. If you look at your list for the nitrate, though, correlates, still soluble. So it's just a little short trick if you want. All right, another example. Bam, I just already told you, anything attached to ammonium will be soluble. But check your list for the anion. Go find carbonate on your list. It states that salts of carbonates, phosphates, chromates, sulfites are insoluble, meaning they don't dissociate, except for those that are attached to group 1A and ammonium ion. Well, that is the ammonium ion, so it is soluble. It is an exception to the carbonate rule. This guy will dissociate into the ammonium ion and the carbonate ion in basically a 2-to-1 ratio. Magnesium carbonate. Okay, magnesium's not part of group 1A, so I can't use that little short trick I just taught you. That means I'm going to have to go to my solubility list and look up carbonate. According to the solubility rules, the salts of carbonates, phosphates, chromates, sulfites, and I'm just reading it right off the list, are insoluble, meaning they will not dissociate into ions, except for group 1A and ammonium ions. Well, magnesium is not group 1A, nor is it the ammonium, so this particular carbonate is going to be insoluble in water and will not dissociate into its ions, will stay a solid. Sodium acetate. Salts of the acetate ion, which that sodium acetate is, are soluble except for silver acetate. That's not silver acetate, therefore it is a soluble salt. And a soluble salt dissociates 100% into its ions, its representative ions. Remember, these are aqueous. This is what's happening in water. All right, try this one. Well, I just read you the rule for the solubility of the acetate anion. Salts of the acetate ion are soluble except for silver acetate. So this guy is going to be insoluble. All right, try the rest on your own. Put it on pause and see if you can determine if these are soluble or insoluble based on solubility rules or the little trick I just gave you about group 1A and ammonium. All right, here are the answers for the remaining one. Sulfates are soluble except for, that means these are insoluble, calcium, strontium, barium, lead, 2, or silver sulfates. Well, I have barium sulfate staring me in the face, so it's insoluble. The next one, sodium sulfate. Well, there's sodium and there's sulfate, done, soluble. Aluminum sulfide. Salts of sulfides are insoluble except for those of group 1A and 2A, and ammonium ions. Well, aluminum sulfide is neither 1A, 2A, or ammonium ions, so the sulfides are insoluble except for. That is not one of the exceptions, therefore it is insoluble. Magnesium sulfide, well, that's one of the exceptions to the rule, so that magnesium sulfide is soluble. And the hydroxide ones, the hydroxides are insoluble except for group 1A, strontium, calcium, barium, and ammonium. That's copper. That is neither 1A, strontium, calcium, barium, or the ammonium ions. That's how you use the solubility rules. All right, predicting products. You've done this already. We've learned how to write ionic formulas. We've learned how to recognize double replacement reactions. we've learned how to predict the products of a double replacement reaction. Now with the solubility rules, we are going to be able to indicate the states of matter of the products of a double replacement reaction. And of course you already know everything has to be balanced, so that's a given. So I am going to do some examples. Gee, I do miss Mr. Kane though. I like the banter. I've got no one to talk to. So I'm going to do some examples for you on predicting the products, predicting the states of matter based on the solubility rules, and of course I don't need to practice balancing. You know how to do that. So here's my first example. Solutions. Solutions indicate a salt in water, so aqueous. Solutions of silver nitrate and sodium acetate are mixed together. Here are your two reactants. Write the entire balanced chemical reaction, predict the correct products, and predict the right states of matter based on solubility rules. So we've done prediction of products before. States of matter is the new one with the solubility rules. So silver nitrate, silver being Ag+1, silver is a transition metal, but it's an exception to the rule. You don't need a Roman numeral in the name. Nitrate is my polyatomic, sodium is in family number 1, acetate is C2H3O2 with the 1-. If I write these reactants appropriately, I will have... These are the correct reactant formulas of both ionic compounds in water. Now I'm going to predict the products. The silver nitrate and the sodium acetate switch dance partners. That's the usual analogy they use for double replacement reaction, which you're familiar with. We've done this before. All right, I've switched them and I've written the formulas correctly. Now I'm going to predict the states of matter and see if a precipitate reaction occurred. Please remember that a precipitate is when a solid forms after pouring together two solutions of soluble salts poured together. Do they or do they not make a precipitate? Well, based on solubility rules, acetates are soluble except for silver acetate. So this is insoluble, meaning it will form a solid, meaning it will form a precipitate. Sodium nitrate. Nitrates are generally soluble without exceptions, so this is aqueous. So I have a precipitate reaction occurring. Balance it. Well, it just so happens that as written, it is balanced. So here is my double replacement precipitate reaction in all its glory, balanced, written out. What you're also going to learn is this is called the molecular equation.